let's make sure that we learn about this and then see how the gaming goes. We have 2 points on the list left. Now I gave you, maybe it went a bit rapid, how we came from the theorem on sampling distribution for the mean to the actual method. Now we will spend a few minutes about how to actually formally interpret this confidence interval procedure, and then next time we'll get back to it again with a different additional interpretation. And this can pose challenges sometimes. The confidence statement, this 95% confidence, is actually something that has to do with a repeated sampling interpretation. It's kind of a meta probability in a way, that this is the procedure, the confidence interval procedure will contain the true value mu 95% of the time that we are using it. We never know whether in the actual case we are right or wrong, but in the long-term run, we will be right in 95% of cases. That's the interpretation of this confidence. And to be formal about it, the confidence interval means that the probability of the standardized error we make will be within, this is actually just exactly what the theorem is telling us, that if we have this t.0975 here, and actually it's minus t here, 0.975, then this one is in here 95% of the time, which is equivalent, in fact, exactly to the confidence interval statement here. I'm not going to do those steps. I mean, you can multiply this on the other side and you can move around, and it's mathematically equivalent to this statement here. So the confidence interval is actually random in 2 ways. The procedure, this confidence interval procedure, is random in 2 ways. It's random in terms of the mean, and it's random in terms of the standard deviation, right? If I do another sample of 10 persons tomorrow, I get a different mean and I get a different spread, right? The mean is different and the spread is different. So repeated confidence intervals will change on their position, and it will change on the mean. I thought about whether I should do this or not. This is a 1975 dance we did. That's pretty much, I mean, from 1975 until 1985, this is how we danced, right? We had really great parties. Maybe you were more advanced. Where I came from in Jutland, this was the dance from 75 to 85. I don't know where you came from, but that's where I came from. This is how we danced. In 85, we got to beers, and then it changed a little bit. But then, 85, that was before. Anyway, if nothing else, maybe if I can make you remember the confidence intervals, the 75 Jutland dance, pretty good music back then also. We didn't have to do anything else on this. It changes in terms of position and spread, right? The 75 Jutland dance, that's a confidence interval. You throw out that, you don't know if you hit the truth, but you do that, you capture the true mu in 95% of cases. Now I did it again. Here it is, put in with a bit of typo there. That's the confidence we have in the confidence interval. We don't, it's a bit, I'm not going to start out exemplifying all the wrong ways of saying this. Actually, I'm just going to say, if you Google, you can find a lot of behavioral and statistical cognition research. Whoa, yeah. There are psychologists that do research in statistical cognition. What would that mean? Yeah, that means to investigate how well do people actually understand statistical concepts. Actually, the Nobel Prize in Economy, Daniel Kahneman, he made a very nice book, Thinking Fast and Slow. Anyone knows that book? Nice book. If you read that book, he made his work that he got him the Nobel Prize in Economy, although he's a psychologist. His motivation for doing the work that gave him the Nobel Prize in Economy was his own personal and his intelligent colleagues at the university, I think in that time in Israel actually, was problems of understanding statistical concepts like hypothesis testing that we will learn next time, and confidence intervals as we are learning now. Those two things are closely connected, and the probabilities and the confidence statements here are related. That is actually very difficult concepts, and I think we likely have all our personal understandings of that, and that's not a problem with me. As long as you can solve my exercises, you can have your own personal interpretation of what these things mean. Maybe you shouldn't always say it out loud. Just be happy inside if you have a good feeling. Don't change that. Keep that happy feeling, and maybe don't follow, maybe don't Google. Don't Google this. It's not worth it. Or do it. It turns out that when you sample intelligent researchers in the world, psychologists, biologists, and even statisticians working at industry, most people don't really understand. But you do, of course. You do, of course. No, it's just to say, if you struggle a little bit with this, then you're not the only one in the world, right? These are difficult concepts, really concepts of probability, if you think about it. It's actually difficult concepts to really understand what those are. And the thing is, there are different schools for how to think about probabilities. There's the Bayesian schools and frequentist schools. Most classical taught courses like this is based on the frequentist perspective, as here, but there are other perspectives. So it's pretty difficult concepts. Anyway, let's see whether we are completely off in the gaming. We're on, but difficult. Difficult. The standard deviation is 6. Root n is 3. That makes the number 2 when you take s and divide by root n. And then you should have the t quantile roughly. So it's roughly twice the distribution. You saw it would roughly twice, and that was the blue one. That was a difficult one. You had really to think clearly. Most of you did. Good job, Baguette. I'm sorry, that's the power I have. I don't want to see this stupid stuff on the top list here. There you are. So we have one more thing on